This section is part of the module 1, but I thought it would be probably worth to separate these sections from the main module 1, as it is more optional for this DCNM essential overview. So it depends on you, right? So that's the reason why I have created a separate sub module 1 just for VXLAN EVPN overview that you can watch if you want, right? So okay, so now let's start. Thank you. VXLAN EVPN, a quick overview. The goal of this section is to review the basics of VXLAN EVPN. Some of you may find the following slides a bit boring, some others may find them useful. Nonetheless, the goal is that at the end of these sections, we have all the necessary knowledge when we talk about different components related to VXLAN EVPN fabric, such as the underlay, overlay network, bump traffic, VTEP, MP-BGP, VPN control plane, etc. Right, and the reason is because DCNM makes a lot of references to these components. I'm sure that most of you are aware of the evolution that we already presented since many years with the concept of the closed fabric. But let me summarize these evolutions again. The network architecture model you have been working on for many years has moved away from the legacy scale-up hierarchical design to integrate a more cost-effective scale-out and distributed architecture. If you think of the Nexus 7K or Cat 6K, for example, traditionally the modular switch chassis have three different elements. First is the supervisor for configuration and control. The second element are the line cards, where you would connect the hosts, switches, and routers and other endpoints at different speed and media type. And you have the backplane, which in case of the Nexus 7K is called fabric modules. As you would configure your network on a port-by-port basis, you may certainly come with a bigger switch than what you really needed initially. And then if you run out of port, you would buy and provision another switch independently. And this is how we used to scale up with the traditional network. With VXLAN Fabric, you disaggregate that model into multiple switches. This allows you to start small and grow as your business needs. First, instead of the supervisor module, you leverage a control plane which is distributed across all switches, which relies on the MP-BGP address family EVPN protocols. Then the leaf nodes are basically equivalent of your line cards, and the spine layer emulates somehow your backplane. This allows you to scale out horizontally on any layer while having always the same distance between leaf nodes, right? The number of hops. You can provision the VXLAN with its control plane EVPN manually, or you can program the whole fabric automatically using DCNM. And there are leaf nodes that exist in multiple sizes and flavors in terms of port density, speed from 100 meg to 400 gig. So just pick the model that matches your need, add it into your fabric, and DCNM will automatically discover it, deploy it, and manage it centrally. This way, your fabric can scale to hundreds or even thousands of switches with multi-site. So you can start small and add leaf nodes as you need without impacting your oversubscriptions ratio. So any enterprise can benefit from it. This being said, the VXLAN data plane provides the network segmentations with the virtual tunnels established between the leaf nodes. It offers natively the IP mobility and scale out. The layer 2 segments are extended over the underlying network infrastructure. And in addition, the VXLAN offers seamless integration for either physical or virtual devices. The VXLAN overlay transport is standard RFC compliant with the RFC 7348 that interoperates with other vendors. VXLAN uses IP-UDP encapsulations that leverages a layer 3 transport offering equal cost multipassing, ECMP, if you will. And as a result, all links are forwarding with a fast recovery mechanism in case of failure. And there is no need for trunking, nor any spanning tree protocols to manage the forwarding state of the links. The VXLAN overlay is a layer 3 transport agnostic. The underlay is used to establish the reachability between the virtual tunnel endpoint, the VTEP, and it supports different type of layer 3 transport. The VXLAN identifier is built with 24 bits, so that allows the namespace to be increased to up to 16 million of identifier. The network infrastructure running underneath is a pure layer 3 network. This is what we call the underlay. The primary purpose of the underlay network is to advertise the reachability of the VTEP as well as the BGP peering addresses to establish and to carry the overlay networks. All interfaces in the underlay are routed interfaces, and they rely on the dynamic routing protocol. Traditionally, we use IGP such as OSPF and ISIS. This is a Cisco recommendations. A slight note here to clarify this. Nonetheless, it is possible to use BGP for the underlay, right? But you need to consider this as a rare use cases and just think before why you want to do that BGP for the underlay before you deploy this, right? This option is not covered during these essential modules. However, it will be discussed during the advanced module series later on. VXLAN is the overlay network that extends the layer 2 connectivity over the layer 3 underlay, which was discussed. So this is the encapsulated network, right? And it is encapsulated with an IP-UDP header. VXLAN allows to establish overlay layer 2 and layer 3 connectivity, but not only layer 2. You can leverage VXLAN EVPN as an IP-based options, an alternative to MPLS VPN, if you will, in order to extend multi-tenant layer 3 connectivity only, if you will. Each VNI is an isolated virtual network. Usually it is called a bridge domain, right, BD. Each switch that participates in the VXLAN has a special interface called the VTEP, right, the virtual tunnel endpoint, which terminates or initiates your tunnels, your overlay. The VTEP provides the connectivity between the underlay and the overlay network. The VTEP is the device that does the encapsulations and de-encapsulations. There is one unique VTEP device per switches, which is associated with its network virtual interfaces. Traditionally, it is the network virtualization edge, and we call it the NVE. And usually we use the NVE1 for the configurations. This is the logical interface where the encapsulation and de-encapsulation occurs. The VTEP supports one or multiple VNI, and each VTEP interface is numbered with a loopback IP address, and traditionally we use the loopback 1. A slight reminder. The classical LAN 802.1q identifier is built with 16 bits, which offers 4,095 different VLANs. And each VLAN has its own unique identifier. And the VXLAN identifier is built with 24 bits, right, offering up to 16 million of segments, as we already said. And each virtual segment has its own and unique VXLAN network ID, the VNI. A VTEP is required on each leaf node where the .1q handoff is initiated. In this example, the host is attached to leaf 1 using VLAN 100. The VTEP maps the outer VLAN 100 to the VXLAN ID 9001. The VTEP strips off the VLAN tag before its encapsulation and adds in the outer header the source IP address of the local VTEP, what we call the ingress VTEP, and the destination IP of the egress VTEP, the next layer 3 hop where the destined endpoint has been learned. The outer Ethernet header has the source MAC of the source VTEP and the destination MAC of the immediate layer 3 next hop. As destination, the egress VTEP encapsulates the VXLAN header and adds the VLAN tag configured for the mapping given at a particular VTEP on the particular leaf node. As a result, the VLAN ID is locally significant. It does not have to be the same VLAN ID from end to end. Although the layer 3 broadcast domain is being extended over the fabric, which is what we call the bridge domain. The BGP address family EVPN is responsible for the control plane. The control plane is responsible to learn the reachability information, the MAC and IP addresses of each endpoint, and to distribute this information across all leaf nodes of interest. In this example, host A wants to communicate with host B. The first step is that the data packet hits the first hop. And now there are two options. First option, the traffic is deployed without control plane. That means that the endpoint learning process to discover the distinct MAC addresses is achieved with a data plane using a fluid and learn handcheck mechanism. With the second option, the fabric is deployed with the EVPN control plane, and then the MAC address and the IP addresses are learned and distributed by the control plane across all leaf nodes of interest. We recommend you to leverage the MP-BGP VPN address family control plane to reduce drastically the flooding of traffic across the fabric, right? And obviously, all these essential modules relies on the EVPN control plane learning, not the fluid and learn. Leaf node 1 makes a lookup in its host table to find the next hop, the egress VTEP, and found that host B sits behind VTEP 2. As a result, VTEP 1 encapsulates the frame received from host A into an IP data packet with as destination the IP address of the VTEP 2 and send it to VTEP 2. VTEP 2 encapsulates the IP data packets and send it to host B, right? As simple as that. The control plane is responsible to learn and distribute the endpoint reachability information, the MAC and IP, across all the leaf nodes concerned by this information. And actually, it's all the leaf nodes that share the same network. Therefore, the control plane minimizes the flooding, as we said, from each node to discover the location of each endpoint of interest. The standard-based overlay VXLAN is assisted with the standard-based control plane, right, as known as the EVPN, the REST family for MP-BGP. And EVPN relies on several standards. So we have MPLS RFC 7432 and overlay NV03 RFC 8365. The address family EVPN is then de facto the choice of for the control plane, as it allows the distributions of the layer 2 MAC addresses and the layer 3 informations using the MP-BGP. EVPN is just one of the address family available with multi-protocol BGP and MP-BGP. So MP-BGP VPN is a mature protocol because actually it is being used by various data planes such as MPLS, provider backbone, PBB, and VXLAN overlay. EVPN offers integrated routing and bridging for optimized forwarding in the overlay, such as the bridging, the MAC mobility, first hop and prefix routing, distributed Unicast gateway, what we call the DAG as the acronym, and multi-tenancy. In this example, the host A is attached to the edge device, the VTEP v1. The VTEP v1 advertises the host A reachability information toward the route reflectors using the EVPN route type 2. And sometimes you can read RT2 in the documentation. So the route type 2 carries the reachability information required for an efficient data packet transport. The first, the MAC address is mandatory, and the IP address in case the fabric is configured in layer 3 mode. And there are additional route attributes advertised, such as the MPLS label 1, which is the L2 VNI, and the L3 VNI, which is the MPLS label 2. And the next hop, which is the egress VTEP and the extended communities. Each VTEP advertises the reachability information, the MAC and IP addresses of the local endpoints using the MP-BGP route type 2 toward the route reflectors. The route reflector will distribute the endpoint MAC and IP addresses to the other VTEPs of interest, which means the ones that are sharing the same networks. As a consequence, all concerned VTEPs have the reachability information of all endpoints with, as a next hop, the location to reach them. So either the endpoint is local, meaning that they have been learned using the host mobility manager, HMM, or it is attached behind an egress VTEP, a remote VTEP, then they are therefore be learned using MP-BGP EVPN control plane. VXLAN comes with a particular transport for the bump traffic. The bump traffic includes the broadcast packet, the unknown unicast, and the multicast data packets. Bump traffic can use multicast protocols such as ASM or BDIR, and in case of multicast transport, a multicast group can be assigned to a particular bridge domain, or layer 2 VNI if you will, or to a group of bridge domain, for example, all layer 2 VNI that belongs to a particular VRF. When the bump transport uses a multicast protocol, the initial data packet is sent only once, and a single copy follows the multicast tree to reach all the final destinations. VXLAN also supports the ingress replication as an alternative method to replicate the bump traffic to all destined VTEP of interest. Ingress replication is a unicast-based replication. Sometimes it is called head-end replications. Some customers may not be comfortable deploying multicast in their data center fabric for any reasons. Those they can use the unicast-based ingress replications. In case of ingress replication, the ingress VTEP for every bump packet makes as many copies as concerned NIF nodes exist and sends them as individual unicast packet toward the respective destined VTEP that have the associated VNI membership. The ingress replication relies on the hardware scale capability. It is traditionally less efficient than multicast because of the number of copies it needs to replicate. In addition to the endpoint, the external routes need to be advertised as well within the fabric. So in this case, the VTEP v1 advertises its local subnet through redistribution of direct connected, static or dynamic learned routes. It includes the IP prefix length, and layer 3 VNI. The IP prefix redistributions uses EVPN route type 5 for that purpose, and additional route attributes are advertised, such as the MPLS label used for the layer 3 VNI and the extended community. And traditionally, the IP prefix learning is achieved via the BGP with VRF Lite. This is known as the inter-ICE option A. In this example, the VTEP V1 participates in external peering with LIS, BGP, OSPF, etc., and advertises the learned IP prefixes from there into the fabric with the IP prefix length and layer 3 VNI. The distributed Unicast gateway function, the DAG, is a great evolution for the SVI placement. Instead of centralize the default gateway in one pair of routers, it offers the same default gateway across all edge switches. And each endpoint can use its local VTEP as layer 3 first hop and as a default gateway to route traffic outside its IP subnet. Additionally, the routed flows between endpoints connected to the same leaf nodes can be directly routed at the local leaf layer. All leaf nodes share the same gateway IP and MAC address for a given subnet. The DAG is always active on each first hop router, the leaf nodes. There is no redundancy protocol, no FHRP filter, no LO exchange required for such layer 3 or routing deployment. The Unicast gateway MAC is defined globally to each VTEP for all VNIs and for all tenants. There is one single virtual MAC address shared between all VTEPs. As already mentioned a few slides ago, EVPN supports integrated routing and bridging, the IRB, and the IRB addresses the inter-subnet communication between endpoints, host or virtual machines that belongs to different VXLAN layer 2 segments. This is also known as the inter-VXLAN routing. The VXLAN EVPN offers natively the distributed layer 3 Unicast gateway functions, the DAG, with the integrated routing bridging feature. IRB also addresses the intra-segment communication or bridging when you need, and bridge traffic use layer 2 VNI. The VLAN ID is locally significant. The shared network transport is actually the layer 2 overlay segment extended between the two VTEP, right? And the return traffic use always the same layer 2 overlay network, the layer 2 VNI. Nexus switch platforms implements the symmetric IRB for its scalability advantages and simplified the layer 2 and layer 3 multi-tenancy support. With symmetric IRB, both the ingress and egress VTEP perform the layer 2 and layer 3 lookups. Routing is only required when endpoints reside in different network intra-tenants or intra-VRF. When a packet is sent from network A destined to network B, the ingress VTEP routes the packet to the layer 3 VNI. The ingress VTEP rewrites the inner destination MAC address to the egress VTEP router's MAC address and encodes the layer 3 VNI in the VXLAN header. After the egress received the encapsulated VXLAN packet, it first de-encapsulates the packet by removing the VXLAN header. Then it looks at the inner packet header, performs a layer 3 lookup, and sends it to the destined endpoint, right? So the layer 3 VNI in the VXLAN header provides the VRF context in which the routing lookup is performed. Only one layer 3 VNI exists per VRF context that each VTEP can use for routing transport, right? So the routed traffic uses the transit VNI, the layer 3 VNI. So the multi-tenancy concept. MP-BGP EVPN offers the multi-tenancy requirement for the VXLAN EVPN overlay, right? So multi-tenancy is a mode of operations where multiple independent instances of a tenant, layer 3 VRF, layer 2 VLANs, operate in a shared environment, right, which is the VXLAN BGP VPN fabric. And that ensures the logical segmentations exist between each instances. The tenant instances, such as a VRF and the VLANs, are logically isolated, but physically they operate on the same fabric, right? So you can have multiple layer 2 VNI per tenant, and there is one layer 3 VNI per tenant, right? So per VRF, if you wish, for routing purposes. So where here the VNI X is used for routed data packet for the tenant 1. In the VXLAN EVPN fabric, a layer 3 VNI identifies, each tenant at the layer 3 level, right, associated with a unique VRF. Wanted to make sure this is clear. That means actually that a tenant in the context of VXLAN EVPN is the representation of a VRF, right? So a tenant equal a VRF in the context of VXLAN EVPN. And belonging to a layer 3 segment, there is a one-to-one mapping between each VLAN and a unique layer 2 VNI within the fabric. So typically, a layer 2 VNI is associated with a single IP network, while a tenant, a VRF, can contain multiple layer 2 network. And the VXLAN EVPN offers the support for multiple tenants or VRF with each a unique layer 3 VNI and layer 2 VNIs, by the way. Okay, so I hope this section was helpful to follow the next series of modules covering DCNM 11. Thank you.